Calculus is the mathematical study of continuous change. While algebra solves for static unknowns, calculus allows us to model dynamic systems. It consists of two major branches: derivatives, which measure rates of change, and integrals, which measure accumulation. From planetary orbits to economic models, it is the language of the modern world. Before we can calculate change, we need the limit. A limit asks, what value is the function approaching, even if it never quite gets there? It is the fundamental building block that makes both derivatives and integrals possible, bridging the gap between discrete algebra and continuous calculus. A derivative represents the instantaneous rate of change, essentially the slope of a curve at a single specific point. Imagine a tangent line touching the curve just once. The slope of that tangent line tells us how fast the function is changing right at that moment. Calculating derivatives doesn't always require long limits. We use shortcuts like the power rule. If your function is x to the power of n, the derivative is n times x to the power of n minus 1. For example, x squared becomes 2x. The exponent comes down to the front, and the power drops by 1. One of the most powerful uses of derivatives is optimization, finding the maximum or minimum values. Because the slope is 0 at the very top of a hill or the bottom of a valley, we can solve for where the derivative equals 0 to find the most efficient solution, like maximizing profit or minimizing material usage. We call points where the derivative is 0 critical points. By testing values on either side, we can see if the function is increasing or decreasing. This first derivative test allows us to map out the behavior of complex functions without needing to graph every single point. Now we reverse the process. Integration is essentially the inverse of differentiation. Geometrically, an integral represents the accumulation of quantities, visualized as the area under a curve. If derivatives give us speed from distance, integrals give us distance from speed. There are two types of integrals. A definite integral calculates a specific number, the exact area between 2 points. An indefinite integral finds the general formula, the antiderivative. Because the derivative of a constant is 0, we must always add plus c to our indefinite integrals to account for unknown constants. Just like derivatives, we have a power rule for integrals. To integrate x to the n, we add 1 to the exponent and divide by that new number. So the integral of x squared becomes x cubed divided by 3 plus c. It is the exact reverse operation of the derivative power rule. This leads to the most important concept, the fundamental theorem of calculus. It connects the two branches. It states that to find the definite integral of a function, you simply find its antiderivative, f, and subtract the value at the start from the value at the end, f of b minus f of a. Sometimes simple rules aren't enough. When we have composite functions, we use u substitution, which is like the reversed Hein rule. We replace a complex part of the equation with a variable, u, solve the integral, and then switch it back. It transforms difficult problems into simple power rule problems. Integrals work in 3D too. By rotating a curve around an axis, we create a solid of revolution. We can calculate the exact volume of these complex shapes by summing up infinite thin disks or washers. This is crucial for engineering parts, creating 3D models, and calculating fluid capacities. Not every function can be integrated analytically. In these cases, we use numerical methods like the trapezoidal rule. We approximate the area under the curve using geometric shapes. The more shapes we use, the smaller the width. The closer our approximation gets to the true value. Finally, we have differential equations, equations that relate a function to its derivatives. These describe how systems evolve. A slope field visualizes the family of all possible solutions, looking like a flow of wind. Finding a specific solution means following one specific path through that field. Calculus is everywhere. Physics uses it for velocity and acceleration. Economists use it to optimize marginal cost. Biologists model population growth, and doctors track drug concentration decay. It is the engine behind the simulations and predictions that drive modern science. To recap, derivatives measure change and slope. Integrals measure accumulation and area. They are inverses, linked by the fundamental theorem. With these tools, you can model, analyze, and optimize the changing world around you. This is the power of calculus.